Hi everyone. As promised, the number of solutions to a system of equations in a couple of examples. Okay? The first example, I have a system of two equations. 9x plus 3y equals 1, and y is equal to negative 3x minus 5. The top equation, I'm not totally sure what that would look like if I graphed it, but the bottom equation, which I'll do in red here, the bottom equation, I know what that looks like because it's in slope-intercept form. So I know it's got a slope of negative 3 and a y-intercept of negative 5. So if I were to graph the red equation, I would go down 5 units on the y-axis, mark that y-intercept, so that's b equals negative 5, and then down 3 and over 1 for a slope of negative 3. And that's more or less what that red equation would look like if I graphed it. Admittedly, that's not a very well-drawn line. But the top equation, I don't know exactly what it would look like, so I might try to solve this system a different way. And I can see here that y in the bottom equation is equal to negative 3x minus 5. And I see that y in the top equation, so if I just substitute in negative 3x minus 5 into that top equation, well, instead of 9x plus 3 times y equals 1, I'll take that variable y and I'll replace it with this new expression, negative 3x minus 5. Okay? And that makes an equation with only x variables in it. So I want to solve that equation now for x. To do that, I'll need to break open these parentheses, so I'll apply the distributive property, 3 times negative 3x minus 3 times 5. Okay, so that's 3 times negative 3x, and 3 times 5 with that negative sign there. So I get 9x minus 9x minus 15 equals 1, and 9x minus 9x is 0, and negative 15 equals 1 is the result I get. That's obviously not true, okay? And that's the kind of situation we get where we've either made a mistake or this system of equations has no solution. I'm a little concerned I may have made a mistake, so I'm going to look a little bit more closely at this top equation, 9x plus 3y equals 1. And I might think to myself, if only I could graph this equation. One way that I like to graph linear equations is to solve for y so that I can see them in slope-intercept form. So I'll subtract 9x from both sides, giving me 3y is equal to negative 9x plus 1. And then I'll divide both sides by 3. So I solve the equation for y, and on the right-hand side I got negative 9 over 3 times x plus 1/3. Okay. Negative 9 over 3 I can reduce to negative 3x plus 1/3. So that y-intercept there is 1/3, so it's a fractional y-intercept, but I'm not super afraid of that because it's just a slope of negative 3, and now I can see it. The slope of the blue equation is negative 3, and the slope of the red equation is negative 3. So you can see this slope here for this equation and the slope here for this equation are the same, and in the graph, those two lines will have different starting values or y-intercepts, but the same slope, so they'll never intersect. So there's never a point that's on both lines, never an xy pair that can solve both equations. Time for a second example. Example number 2 will be this system of equations. 10x minus 5y equals 20, and 2x minus y is equal to 4. Now if you look very carefully at this system, you can choose whatever method you want to solve the system of equations. You could make a graph, you could substitute, or you could use elimination. when I analyze this, I might ask myself, okay, I could maybe solve this equation on the bottom here easily for y, and then use substitution. But sometimes I like to try elimination, so looking at this, if I could somehow, if I could get this to become a 10x by multiplying by 5, that would help me out. Or if I could get this to become a 5y by multiplying it by 5. So something weird might be going on here. I'm going to take this 2x minus y equals 4 equation, and I'm going to multiply it by 5 on both sides in order to try for that elimination move. On the left-hand side, using the distributive property, I get 10x minus 5y, and on the right-hand side, I get 20. And now I should hopefully notice that 10x minus 5y equals 20 is equivalent to the top equation. So I manipulated this bottom equation into the top equation. So these two equations seem to be identical. Okay, so that means I'm thinking that this is going to be a case of infinite solutions. I've got a couple options. I could try elimination. Okay, that's of course what I was hoping for when I multiplied by 5. So I'll do 10x minus 5y equals 20. And I'll draw my golden road. Okay, and I'm going to take the left-hand side of this equation and the right-hand side of this equation, and I'm going to add them here. And I know this seems ridiculous, and it is ridiculous. It's ridiculous because they're identical. Actually, I'm not going to add them. Pardon me. I'm going to subtract them. And this is a little ridiculous. Let's take a look here, okay? So on the left-hand side, I have 10x, and then I'm going to subtract 10x. And then I have negative 5y, and I'm going to subtract negative 5y, needlessly complicated. And on the right-hand side, I'm going to have 20 minus 20. Okay, so on the left, I get 10x minus 10x, which is 0, and negative 5y minus itself. So that's negative 5y minus a negative 5y is a negative 5y plus 5y, which is also 0, equals 0. So I get 0 equals 0. Okay, this is a satisfied equation. Doesn't matter what I plug in for x and y. No matter what I plug in for x and y, it'll give me the same result for the top equation as it gives me for the bottom equation, because they're identical. So just as a quick throwback and reminder to an earlier video, we had an equation that looked like this: 2x plus 3 minus x equals x plus 3. On the left-hand side, I rearranged and then combined like terms to get x plus 3 on the left, and that was equal to x plus 3 on the right. And those things being identical, I, for instance, subtracted x from both sides to get this kind of result. So any sort of result where the left side and the right side are always equal and the equation is always satisfied no matter what I plug in for this one variable, that gave me an all real numbers solution for a single variable equation. It meant that no matter what I plug in for x, the equation is always satisfied. Over here I get a similar type outcome where the left side and the right side are always equal, and that means whatever satisfies the top equation will also satisfy the bottom. Okay, and what that means is there are infinitely many solutions to either equation, and if you were to graph these two equations, you would get the same line in both cases. So there are your two examples. There are more examples linked in the documents posted for today.